Okay, good morning, everybody. Today's session is on drones, and I'd like to present, I'd like to introduce the presenter for today, Smith. So over to you.
Thank you for introducing. So I think we might wait for a couple of minutes for some audience to join.
आम्हाला विचारायला दोन काय रे काय कोर्स सर
काय रे इंडिया की डायरेक्ट आईवर घ्यायची असतं रे मी देत नाही कुठे आहे लिव लिव घेतलं लिव
We request everyone to kindly mute your mic. Suraj Patil, please mute your mic.
Okay, I think we will start. Can I start, Ruchi, Karen?
Yeah, you can.
Cool. I hope I am visible and audible clearly.
Yes, sir.
I will share the screen also. Just give me a quick feedback if the slideshow is visible later. Okay. Is the slides visible in full screen?
Yes, sir.
Thank you so much.
क्या चल रहा है इधर
I request everyone to please mute their mics.
हे हर्ष या सांगितलं
Yeah, thank you so much. So, welcome everyone. Welcome to the technical session on all about drones. So, here we will be just having a brief introduction to the world of drones and usually called quadcopters and in general aerial vehicles. This is me, myself, Smith Kesaria, and with me I have the team e-Yantra. And yeah, I'll just without any other further ado, I'll start. So this is the agenda for today's session. First, we'll see the introduction on aerial vehicles. Then specifically out of aerial vehicles, we'll see about something about quadcopters. That's what we usually see around us. Quadcopters and their workings. Then we will also see how to make your own quadcopter. We might also see what are control systems in general and how are they applicable in the scenario of quadcopters. Then we'll see some kind of high level planning that is involved and some usual applications of the quadcopters. So that's about what's the agenda. So first thing is, let's jump direct into the first thing, which is introduction to aerial vehicles. Now my question to all is, what comes to your mind when you see or hear the word drone? Is it the first picture that comes to your mind when you hear the word drone? Is it the second picture or the third picture? Maybe all, right? Maybe all, because first is the most common that we see around us in maybe weddings, in concerts, in recreational flying or hobby flying or cinematography. And second is mostly seen in industries, film industries, and yeah, professional enterprise applications. Third is more like not so kind of commonly available picture in your mind when the drone comes, but still some of you might think this as a drone. But this thing, does anyone think of this as the word drone when it comes to your mind? No, right? But let me tell you, this also is a drone. So in general, how can we define the word drone? Drone is a pilotless aircraft directed by remote control or nowadays even autonomous. So in general, if you don't have a pilot and if it's flying by its own self, by a remote or autonomously, it's called a drone. It might be a ground vehicle, it might be aerial vehicle, it might be underwater vehicle also. But usually we denote the term drone as with aircrafts. So the word drone, aerial robot, aircraft, multi-rotor, quadcopter, all these things will be used interchangeably throughout the session that we use, that we have here. And even you can usually use those terms. So since we saw these random images and very diverse images of drones, let's just classify aerial robots into some categories, brief categories. First one we'll classify into is multi-rotors, the class of multi-rotors. Now again, the question comes to is, what is multi-rotor? Simply, if you break the two words, multi and rotors, you see there are multiple rotors, more than one, which is multiple rotors. They look something like this. Then we have winged aircrafts or aerial robots, which have fixed wings. The difference between the first one and the second one is here, the wings, these propellers that you see are also wings, but they rotate. They rotate at a particular RPM to generate the lift or the thrust that we call. But here, they do not rotate. These wings do not rotate. They are fixed wings. And since they glide in the air with high speeds, they produce lift or thrust. So fixed wings and the rotary wings. So first is multi-rotors, where you have multiple rotorcrafts, rotor bodies generating thrust. And second image that we see is a fixed wing aircraft. There are some also, if you combine both of them, there's something called as a hybrid class of aerial robots, where you have fixed wing also as well as a combination of rotary wings. So you can have 3, you can have 2, you can have 4, or even more, as well as fixed wings. So you have advantages and features of both the classes of aerial robots. So this is how I classify aerial robots briefly. There are multi-rotors, there are winged ones, and then there are hybrid ones. So let's see about the specific class multi-rotors and classify them more in depth. Uh, let's classify them on the basis of numbers, that number of rotors that they have. So as we defined, multi-rotors are nothing but a rotorcraft with more than 2 lifting rotors. Out of that, you can have different numbers of rotors, right? So the first one that is most commonly seen around us is quadcopters. Now, as the name suggests, quad means there are 4 motors, and copters again is a word for a rotating body. So quadcopters as the name suggests, it has four rotors generating lift or thrust, and then there are hexacopters. Hexa means 6, so I think nothing new. 6 copters, 6 rotors. There can be more. There can be octocopters. This particular aircraft has eight of them, and also you can reduce the numbers and go to bicopters or tricopters. So in bi we have 2, tri we have 3. So now the question is, why so many variations? Why so many difference? If you can achieve with, let's say, 4 rotors, why do you want to go to 6? Why do you want to go to 8? Even go under below, having 2 or 3. So the answer is basic. It's just simplicity and the level of complexity involved in all the aspects, in manufacturing, in making, in controls, in softwares. Just a reminder again, please mute your mics. Actively check your mics are muted or not. Thank you. So as I was saying, why quadcopters, if they are present, why do we need other ones? So since if you don't want to make your life more difficult or make it more complex, or if you don't have any specific needs, I'll come to what needs, but then you can have just 4 rotors, because making is very simple, control is very simple, and stability, agility is also possible. Whereas octocopters and hexacopters, they are more over actuated. They do the same job as a quadcopter, nothing much, but still, why do they have more actuators then? So answers can be, if you want to lift more payload, okay, maybe yes. If you want to lift heavy weight, or maybe go for a longer duration, so have a bigger battery, so you can have multiple rotors adding up the thrust, or you can have redundancy. For example, if one of the motors in in our octocopter, because of some reason just it breaks or motor fails, you can have redundancy. You can still control the aircraft. It will not crash. It will not go haywire here and there. And since it's a complex control architecture inside that, it will manage itself and keep itself stable. So redundancy is also possible. And if you want more agility, more payload capacity, then definitely you can increase. Now the question is, if it is possible by bicopter and a tricopter, why even go more than that? The answer is, again, if you go below 4 rotors, somehow again the complexity increases. Now you have so many degrees of freedom. You have to move front, back, top, down, rotate in the roll axis, in all the axes. With just 2 rotors, not possible. With just 3 rotors, maybe you can have certain degrees of freedom. Maybe you can have uncontrolled degrees of freedom over the other degrees. So again, complexity increases there. So as a sweet spot, usually quadcopters are mostly used around and seen around. So this is a brief introduction about the classification of aerial vehicles, aerial robots. We saw there are rotorcrafts, multi-rotorcrafts, wings, and hybrid. Among the multi-rotors, we have classification among the numbers of rotors that we have. Yeah, okay. So let's now zoom into what are quadcopters and how do they work. Okay. Just make sure you don't disturb others while you are attending the session by not muting your mics. Okay. So yeah, I was talking about, let's see about quadcopters and their workings. So since we saw multi-rotors, a lot of aerial vehicles, among that we saw multi-rotors, among this, we will see into quadcopters. So first thing, very brief, very simple, is they have 4 motors, since the name suggests. And usually they are placed in a square shape. If you look carefully, the distance between 1 and 2 and 1 and 4 is the same as 4 and 3 and 2 and 3 and such. So this is a symmetric square, not a rectangle, not a trapezium. Usually it's found in a square, to keep it simple. And they rotate, obviously, to generate thrust or lift. Now, the fashion that they rotate is very specific. If you see, number 1 and number 3 have a direction of clockwise, and number 4 and number 2 have a direction of anti-clockwise. They are also color coded in green and blue. And also they are kept very specifically, they are paired very specifically, as diagonally opposite motors rotate in the same direction, and the opposite diagonally rotates in the opposite direction. So we'll see why it is done, but usually this is what the trend is followed. You can have, obviously, interchange the green and the blue ones. For example, the green ones are here, the blue ones are here. You can change them. The blue ones or the anti-clockwise ones can be 1 and 3, and similarly 2 and 4 can be clockwise. That can be possible. That doesn't make any difference. So the point to note here is one thing: the diagonally opposite rotors rotate in the same direction, whereas the opposite diagonal rotates in the opposite direction. That's clear. So in a brief, this slide just tells us there are 4 motors usually placed in a square configuration, symmetric configuration for simplicity, and also they rotate in a particular fashion. So 2 of them rotate in a clockwise and other two of them in the anti-clockwise direction. So now let's see, the point is, okay, we got to 4 motors, we connected them. Now how do we fly them? How do we fly the quadcopter? How do we achieve motions with the quadcopter? So second side is types of motions possible. Now here we have to remember a rule of physics, basic thumb rule of unsaid rule of physics. That is, you can have at max the n number of degrees of freedom as the number of actuators that you have. I'll repeat, if you have n actuators, you can at max have n independent degrees of freedom. So for example, since we have 4 rotors here, 4 actuators here, at max we can have 4 independent degrees of freedom. Now when I say degrees of freedom, it means movement in one axis, not changing the movement in other axis. So that's a freedom, that's you can move, it's not constrained. And that's what the rule says. If you have 4 actuators, 4 independent degrees of freedom. So what are these motions or degrees of freedom possible? First thing is accelerate. So for this slide, I'll just show you one of the quadcopters that I have lying around with me. Not a different one, it's just usual 4 rotors. So if I keep it here in front, this thing says accelerate. Now if we rotate all 4 motors with the same speed, or even increase the speed with the same amount or decrease, we can have acceleration in the upward direction or wherever it's pointing. If it's pointing here, it will just accelerate in this direction. And if we decrease the thrust compared to the weight of itself, then it will decelerate. So we can have acceleration, deceleration, where we keep all the speeds of all 4 rotors same. So increasing the speed of all 4 will accelerate, decreasing will decelerate. That's one thing, one motion found. Okay, it can go not up and down necessarily, because if it's tilting, now the thrust is pointing in a tilted direction. The acceleration is not purely upwards, it is in a tilted direction. So acceleration confirmed. Okay. Now what is roll, pitch, and yaw? So let us define what are these axes. Some of them might have heard, some of them might have not heard. So in the diagram, if you see, there are 3 axes drawn from the center of the quadcopter. I can still hear some noises in the background. Please ensure if Ruchi or Karen are present, can you please locate them and mute them? That causes a lot of inconvenience. Please be mindful about that. Okay. So as I was saying, roll, pitch, and yaw are the names of the 3 axes in the rotation axis that we can see in the diagram. So there's an x-axis drawn in the red, there is y-axis in the green, and z-axis in the blue one. So if you see, the rotation around the x-axis is termed as roll. Similarly, rotation around the y-axis is called as pitch. Rotation around the z-axis is called as yaw. Let us just imagine what this diagram says. So if this is the quadcopter and this is my x-axis, the lateral one, then the rotation around, sorry, if I'm at, this is the x-axis in the front, rotation around this front axis this way is roll. Okay, because the x-axis is still in the center and it's rotating around the x-axis. Similarly, if the y-axis is on the lateral side, then rotation around the y-axis is pitching. So you can relate it with your head. If you roll right and left, this is called as roll action. If you move up and down, that's the pitch action. And finally, the z-axis, which is coming out of the quadcopter in the top direction, is z-axis. So rotation around that is yaw. This rotation is yaw. And similarly, with the head, we can pan. So this is yaw, rolling, tilting basically, and up and down is pitching. So we have 3 different axes, and now since the quadcopter has 4 actuators, we can have 4 independent degrees of freedom over roll, pitch, yaw, and accelerate. But question is how? Once we saw if we have constants, if we have combined same speed for all the 4 motors is same. If we increase the speed of 4 motors and decrease, we have acceleration, deceleration. Great. How about roll, pitch, and yaw? So if you want to do a roll action, okay, simply if you just increase the thrust produced by the 2 rotors on this side and decrease the thrust on these 2 sides, definitely you have a imbalance in the torque as said on the rigid body. So if you are applying more force on this side but less force on this side, then you can have a tilting action. The rotor will tilt in this direction as there is an imbalance in the force. Similarly, if you want to tilt in the opposite direction, decrease the thrust from these 2 rotors and increase it from these 2 motors. So it will roll on this axis in this side. Anurag says repeat. Okay, I will repeat this slide. So what we see here is what are the types of motions the quadcopter can achieve. The first motion is accelerate. Since we have 4 rotors, 4 actuators, and we have same speeds for all of them. So the speed at which this motor is rotating is exactly same as this rotor, and this rotor. All 4 rotors are exactly same, rotating at the same speed. But if you increase all of them at the same time, you will get acceleration in the pointing axis. If you decrease the thrust compared to its own weight, then it will reduce, the height will reduce and it will start decelerating. Clear? Acceleration and deceleration, where you have all 4 motors at the same speed. Now, as I explained, roll, pitch, and yaw are the 3 angular rotation around 3 axes, which is roll is around x-axis, pitch is around the y-axis, yaw is around the z-axis. So I will just show motions. This is roll axis, this is pitch axis, tilting up and down, and finally yaw is just turning it around. So we saw acceleration can be done by increasing the speed of all motors or decreasing the speed of all motors with the same amount of magnitude. Now, how about roll? If we want to do a tilt action from the quadcopter, simply you just increase the thrust from 2 rotors and decrease the thrust from the other 2 rotors, so that we have an imbalance in the force, and that's why it will tilt because of imbalance. Simple physics. Similarly, if you want to pitch, you just increase the front 2 rotors. This is front for me. So front 2 rotors thrust increases. Similarly, there is not much thrust from the behind motors because we have not let it increase. It will just try to tilt in the upward direction because there's an imbalance in the forces. That's creating a torque on the body, and we have a roll action if you pair these 2 motors and these 2 motors. But if you pair these 2 motors and increase them and pair these 2 motors and decrease them, you have a pitch axis actuation. That's clear. Now how about yaw? Can anyone just guess how do we pair motors or actuators to get motion in the yaw axis? Yaw is again this axis. Can anyone please answer? I want this session to be interactive.
Yeah, actually,
So
for
if
the
you have, okay, tell
yeah,
me.
for actually like the front two motor, the front and the back motors, if they rotate, like the complete orientation of the drone changes.
Front and the back motor rotates in what manner? In what fashion?
Like you're having a drone in your hand, the right one,
Yeah.
right first one, and the left, it's the back, yeah, the back right
Okay.
one.
These two. Okay, diagonally opposite.
Yeah,
How
diagonally
about that?
opposite. Like they rotate and the complete orientation changes. Like if the drone turns towards the left or right.
Okay, so you're saying somehow pair the diagonal. Once we paired the front and back, then we paired the right and left.
Yes.
That gives us roll and pitch. But you're saying diagonally, if you pair diagonally and increase or decrease the thrust, then you can get a yaw. But why?
To change the direction of the operation.
To change the direction of operation. But yeah, still, what physics phenomenon? Since I said there is an imbalance in the force for roll and pitch, what is the physics phenomenon that leads the change in or diagonally opposite rotors to do a yaw axis motion? You are correct. The answer is correct, but I just want more explanation. Can anyone else guess it?
The Magnus effect.
Magnus effect, not really. We don't deal with aerodynamics here for now.
I get it. Yeah.
Can anyone else guess this? As he said, you pair the diagonally opposite motors, but that achieves a yaw axis, but yaw axis motion. But why? There is no imbalance in the torque, right? If you increase these two rotors thrust and decrease these two rotors thrust, still there is a more force pointing at this, more force pointing at this. There is a balance here still, right? It's not imbalanced. Here same, it is decreased. So average thrust is still the same. It will not do your axis. It will do, but why is the question. So here comes the principle of conservation of angular momentum. Since we all have studied basic physics in 10th and 12th, what physics says is any body with finite mass and finite inertia, if it's rotating, it has an angular momentum. Just as we have linear momentum, if we are moving at a speed, you have a momentum, right? Similarly, if a body is rotating at a particular speed, it has a momentum which is angular momentum. Now, if you just consider all of the four motors rotating in the same direction. As we saw, they're all opposite, but no, let's just keep it all the same. Then what will happen is all the four motors have a finite angular momentum in the same direction that they are rotating. But the conservation of momentum says the body has to have a zero or momentum has to be conserved in the world. So to conserve that, to have the imbalance to be balanced, the drone itself, the base itself, will start having a momentum in the opposite axis. So let's say all the rotors are moving in the same direction in this fashion. Then to balance that, to counter that, the base or the drone itself will have a momentum, start having a momentum in the opposite direction, which is movement in the yaw axis. So we are getting somewhere. So that's why if you want a balanced torque or momentum in the z axis and you don't want to move, that is why you have opposite rotating rotors. So since the clockwise are two of them are clockwise, two of them are anti-clockwise, in a normal scenario, the momentum cancels out. The direction of the momentum is opposite for the two rotors compared to the other two rotors. That's why the momentum cancels out in a normal scenario. But just when you want to yaw, you can just, let me just quickly go to the previous slide. So here, if you take, if you just move or rotate all the rotors with the same speed, the 1 and the 3 combined have the same momentum as 2 and the 4, they just cancel out. But if you want an imbalance, you can just increase the 1 and 3, which is the momentum is more than the 2 and 4 combined, then you have an imbalance in the clockwise rotation. Now, since there is an imbalance in the clockwise rotation, the drone or the base has to have a momentum in the counterclockwise direction to balance out the momentum and cancel out. So that's why if you want to rotate or move the drone in the yaw axis, let's say in the clockwise direction, you just have to increase the momentum in the other direction. So that is how conservation of angular momentum helps us to generate a yaw motion. Now also, this is a homework to verify that since I mentioned there are 4 independent degrees of freedom, do they have independence over each other? For example, if we have a motion in roll, is it affecting pitch? Question. The motion in pitch, is it affecting roll and yaw? Or even the question is roll, pitch and yaw changing anything on the average acceleration or the thrust? So if we want to change a particular axis, okay, I'll continue. Yeah. So the point I was making is, do we have to check we should check the independence, right? Since I mentioned it's independent, if I do a roll, it should not change anything in the pitch or in the yaw or in the acceleration axis. Similarly for all of them, if I just want to accelerate, the pairing that I did should not change anything in the pitch, roll or yaw axis. So the homework is to think about the motions that we defined, the combinations that we defined for the rotors do they have any effect on the other axis while moving one axis? Is it changing the other axis or not? So that's why that's how you can verify the independence of degrees of motion. Now, one more question that comes to mind. Okay, we saw about angular movement, angular change or angular motions. We can do roll, pitch, and yaw. That's fine. But we don't want those, right? We don't want in real life. We want the drone to move fast in the front axis, in the back. It should go front, it should go right, left, and it should go up and down. So it does, right? We know, we have seen drones do that. So how do they do that? Since it's not mentioned here, Priyanka is asking what homework. Homework is just after the session, just verify the independence of these four axes. When I mean independence, I am saying if you want to change the roll angle and whatever you are doing, the motions that you are doing, pairing the two motors, is it changing the pitch axis, pitch angle or not? Similarly, is it changing the yaw axis or not? If it's independent, it should not change, have any effect. When you want to just roll, it should not have any effect on pitch or yaw or even the acceleration. So that's how you want to, will want to verify the independence of all the 4 degrees. Now, my question is, okay, angular rotation done, check. But how about going front, going back, coming right, left, and going up and down? So now the problem here is if you want to move front, we don't have a thruster at the back, right? Just like a plane. We don't have something pushing it back so that it goes in front, or something pushing right so that we go left. That's not possible, right? A simple thing is, since we know the acceleration is in the axis, or it points towards the perpendicular axis that comes out from the propellers. For example, if the propellers are oriented at this angle, then the acceleration is in the top axis. If they're just tilted a little bit, the acceleration is nowhere in the top. It's in the tilted axis. So it has a component in the front axis as well as the top axis. So it has a component in X as well as Z. So at this point, if you just rotate a bit and now again do not rotate anymore, lock your orientation at this particular angle and have an acceleration, then it will go in the top axis as well as the front axis. So this is how tilting and then accelerating helps you go front. Similarly, going to the right and then having an acceleration will push the drone towards the right side, or similar to the left side. But if you want to go purely in the direction, up and down direction, just have a 0-degree roll, 0-degree pitch, and then just accelerate. You will go in the up and down axis. So finally, after all this, we have 6 degrees of freedom: X, Y, Z, roll, pitch, and yaw. So 3 translation axis, 3 rotational axis. But still, we have to check the independence. If I want to move in the X axis or the front axis, can I do that without changing the angle pitch? Not possible, right? To move in the front axis, you have to have a rotation in the pitch axis. If you tilt, then only you can go forward. Similarly, if I go the other way around, can you tilt and stay at the same position and hover around the same position? No, because you have tilted, now the thrust is pointing in the front direction also. So you will have a motion going, the quadcopter will start moving in the front direction. That's why these 2 degrees are not independent. The roll and the X, the pitch and the Y are coupled, are entangled. One affects the other. That's how it's not independent. So X, Y are nothing but same thing as roll and pitch. So that is why, since we have 6 degrees of freedom, even though we have 6 degrees of freedom, it can move in front direction, but not independently. That's why the types of motions are just 4 independent motions. Now the question is, okay, we saw how it is functioning, how do we have the motions, but the question is, how does one make a quadcopter, or what it takes to make a quadcopter? So we will list down the components first, and then we will see one by one in the detail. Okay, so that's the list of what you need, what anyone needs to bear as a just a bare bone to essential parts to make a quadcopter. First thing is definitely a chassis, a frame. a structure that holds everything. Second thing is the thing that generates the thrust, generates the lift, makes it go up, down, or do the motions. So propellers. To rotate the propellers, we need motors. To drive the motors, we cannot just connect the motors to our batteries. People who already have interface with motors know that you cannot just directly connect to the batteries because we want to have a changing speed, right? So there are motor drivers that drive the motor. Then there is a flight controller, that is like a computer, an intelligent computer that does some complex calculations, has an algorithm running, and that directs what to do, when to do. It's a flight controller. It controls the flight. Okay, if you want to fly it with a manually piloted aircraft, as a pilot, you have to have a remote control system from your drone and the pilot. Then something which is GNSS receiver. Now, what is GNSS? It stands for Global Navigation Satellite System, a very fancy word for what we call usually as GPS. So GPS is GNSS of USA. GNSS is general term, Global Navigation Satellite System, navigation possible in the global, in the entire world because of satellites. So that method is called GNSS. GPS is the constellation of USA. Similarly, we have constellations from Europe, which is called Galileo, GLONASS from Russia, Baidu from China, and India has its own Navig now. So we will not use the word GPS, but it's called GNSS. So yeah, general term we will use. Battery to power everything definitely, and some software that runs inside the flight controller. As I said, it has to be intelligent. It has to be smart enough to know what to do or what to direct the motors when. So these are the basic requirements if you want to make a quadcopter, if anyone wants to make a quadcopter. So let's see one by one. Frames. So you can either make your own or maybe get inspired from the diagrams or the structures and make your own, or else you can just grab it from your market or online stores. So they come in different sizes and formats. So this one you see in the first one is a plastic frame, generically available in India on different online stores. So this is made of plastic. This is a little more on the premium side. It has plastic plus carbon fiber. It has a landing gear, nice landing tool it has, or maybe completely off carbon fiber. It is purely made of carbon fiber. It has more strength. It has it is not bendable. So this is and obviously sizes can increase from smaller to bigger ones. So you have to choose which size you want to make your quadcopter. Either make your own frame or get it assembled from the market. You can have different materials, plastic, carbon fiber. You can also make it from metal or wood if the weight permits. Next thing is propellers. So how do we see what are the different types of propellers? First we see is a two-blade propeller. We have all seen this. A three-blade propeller is also possible, or maybe four, or even more than that, 5, 6, 8, 10. So the difference is, someone will ask, why if you have a two-blade propeller, why do you need a 3 or 4? In the same size, with the same amount of RPM, if you have more number of wings, definitely your thrust will increase. Correct? Because you have more surface area. We have all seen, right? Our two-blade fan is producing a less amount of airflow compared to a three-blade fan. Even if a four-blade fan has more airflow compared to a three-blade fan, right? We have seen it all in our houses. So with the same amount of size and same amount of rotation speed, a more the more the number of blades, the more the number of thrust. But then the question is, if you have a four-blade propeller, why do you want to use a two-blade or a three-blade? The answer is sometimes you don't want that much power. Sometimes you don't want that much agility. Or even if you increase the number of blades, the efficiency decreases. It will take more power to generate thrust, and that's not efficient. So in different applications, you will choose different ones. In efficient and longer duration ones, not so heavy payload ones, you will choose a two-blade propeller. But if you want a very fast, very quick, very agile drone and to lift a heavy payload, but you don't care about efficiency, you can do a three-blade or a four-blade. Let's see what materials are possible. So one of the materials is plastic. This is injection molded or whatever. This is carbon fiber. It's a different material at all. It has more strength. It will not bend. It will not deform. It will be stiff, or even go for a wooden propeller. So this is not used that much, but just it's available. Next thing is, since you have the propeller, you want something to rotate it, right? Obviously, we need motors. So we'll just have listed about 2 motors. There are numerous number of motors possible, but we will see two of them. commonly available. One of them is called brushed DC motor. DC is direct current. So brushed DC motor, it just directly runs out of a battery or a voltage power supply, a cell, or even a battery. So they come in different sizes and formats. So this one you see is a brushed DC motor. This also is a brushed DC motor. This is more commonly seen in the RC cars. We all might have seen this, right? In the hobby stores, we can find that. And there is something called as a brushless DC motor. So just the simple thing is, difference is the brushes inside are not present. So brushless DC motors look like something like this, more oftenly used in aerial vehicles like a quadcopter or a multi-rotor craft, or these days even they are used in electric vehicles like scooters and cars. So this is one of the brushless motor, and if you open it up, it looks something like this. It has a stator and a rotor. Simply, if you just try to find the meaning of that, stator just stays, rotor just rotates. Something is fixed, something rotates around it. So there's a coil inside the stator with the stator, and there's a rotor that is pure permanent magnets. So having a different kind of electric signals will make the magnets move around. So that's how the brushless DC motor works. And if you have motors, you also have motor drivers. So brushed DC motor drivers look something like this. Usually it's a MOSFET based H bridge, and there are specific drivers for brushless DC motors, also known as electronic speed controllers. A specific name for brushless DC motor drivers, eSI. So these are electronic speed controllers. They are more intelligent, more smart. You just have to direct them. You see there are different wires. Here the red and black are the power supply lines. You can connect the battery here, the DC supply. This red, white and black is the signal wire. You just pass the information about how fast you want to rotate the motors, and these three finally connect to the motor. So in the previous diagram, if you see, there are three motor wires instead of just two in the brushed case. For brush motor, we have two wires. Brushless, we have three wires. So these three wires go inside the motor, and finally you can have an interface that connects to the motor, and you can have a RPM control or a speed control over the motor. So we saw motors, brushed motors, and we saw the drivers for motors, brushless and brushed both. Now next thing is flight controller. So I'll define the flight controller as a computer capable of running complex algorithms which controls the air. So it
Meeting
has
unlocked.
okay. The flight controller is a computer that just runs complex algorithms which controls the aircraft, as we saw. Let's see what are the options possible. Some of you might have seen or heard about these ones. The first one is a Pixar. I think some of you might have heard already. This is an Arduino pilot board, or previously known as the APM board, APM flight controller. This third image, black color image, is more of a less complex version of the flight controller. It's smaller in version, it has less features, but still a flight controller. Also used in some DIY applications. Also, the cost is less, so easily people can afford it if you want to make a low cost aircraft. And finally, I have shown an Arduino also, which is not actually a flight controller, but you can make it as a flight controller. If you want to build your own one, take an Arduino, write an algorithm inside that, have the sensors interfaced, and that's a flight controller. Because all of these are nothing but some microcontrollers interfaced with some sensors and running some code, the firmwares. So these can be chosen as the flight controller depending on the application. So Pixoc, first and second one, are more towards the autopilot side. The third one is more towards the manual side, and fourth one is complete DIY side. Now what? Also, you need a remote control and a receiver because you want to direct the aircraft remotely, right? Not have a wire connection. So this is some kind of remote controller and transceiver. So this is the kind of a remote control, and this is the receiver that can pair with the transmitter and have your signals transmitted to the quadcopter. You also have some advanced ones which have screen on that. So if you have a camera interfaced and the camera is wirelessly transmitting towards your remote control, you can have a built-in display, and see the quadcopter view. I am sure you might have also seen this with the camera drones. Or alternatively, you can just skip all of them and have a mobile application. So somehow if you can connect your mobile phone to the quadcopter either by Bluetooth or Wi-Fi or by internet. And you have an app here that's just like a gaming controller. Then that's a remote controller. So if you see, there are two kind of joysticks here. You also have two joysticks here. You have different buttons, different sliders, different toggle switches. You also have different buttons, sliders, and toggle switches. So it's like a software version of the remote control. This is what we had built here in eYantra. In fact, our interns had built this as a part of summer internship program. So this is a kind of things that we do here or develop here. So you can have this kind of apps, have it connected to your quadcopter in any manner you like, Bluetooth, Wi-Fi, or even internet, and control the drone or quadcopter. Okay, done. Now what? Now the drone has to have some sensors, right? Sensors to know its position in real time, know its own orientation in real time. So as I mentioned, Global Navigation Satellite System, GNSS, in general known as GPS, or GPS is a specific thing of specific GNSS of USA. So that's a receiver that we need for the quadcopter to know its own position in the real world. They look something like this. Also come in very small form factors like these, or can be advanced. So the last one is a more complex and expensive model of a GPS or a GNSS receiver that gives you more accuracy. So you have these kind of different. You can just go into onto the online stores and check what kind of options are available for you. Batteries, since the power is needed to fly or to run all the applications or the peripherals, we need power supplies. So this first option is a lithium polymer battery. We have all heard about lithium polymer batteries, usually found in power banks, laptops, electronics like mobile phones, or even watches. Lithium ion batteries. Little difference between polymer and ion battery. Usually the lithium polymer batteries usually come in higher power delivery capacity, and these are more of a long running batteries. Lithium ion, lithium polymer, and the final ones are like a normal cells that we use but rechargeable. Nickel metal hydride is the one. The chemical composition is nickel metal hydride. So lithium polymer, lithium ion, nickel metal hydride, depending on your application, you can choose any of them. But usually 90% of the cases use lithium polymer batteries for quadcopters or drones because they need high discharge rate capacity. We saw the hardware components required. Okay, that makes it. We have a frame, we got propellers, we attach it to our motors. For the motors, we got drivers. For the drivers to communicate, we got a flight controller. And also we got a receiver for the flight controller to know where the drone is right now. Also, we added the battery as a hardware component. Done. Makes the complete system ready. But what about the software? That completes the hardware aspects, but software aspects are still missing, right? You need a software or a firmware that actually runs inside the flight controller. Just a second, I can still hear a lot of noises in the background. Okay, we were at the point of software of the flight controller. As we said, it has to run complex algorithms to make the quadcopter control, right? So the softwares possible, if you don't want to build your own ones, are PX4 Autopilot, one of the ones that we usually have heard about. Autopilot, again, a very commonly known term in the ecosystem. Not so commonly known are Betaflight or iNav. The last one is least known. And Betaflight and iNavs are more towards manual flight, manual piloting, fast aircrafts, racing drones. And the ones on the left, PX4 and Autopilot, are more towards the autonomous flights. So if you are building an application where you have autonomous flights, you will definitely choose one of them, which is PX4 or Autopilot. is my, I think my screen was not visible. Is the screen visible? No, right? Okay. So I was at this slide. You will most likely choose a PX4 based flight controller software or an Arduino one if you are going for a autonomous application or autopilot application. Whereas if you go for manual ones, you will either go for Betaflight or iNav for planes usually. iNav is for planes, Betaflight is for manually flown acrobatic aircrafts. Yeah. So now let's proceed further and see what are these firmwares or what do these firmwares actually do. So we have to first think about we have to first learn about control systems. Now some of you might have been might have studied this in your bachelor's or even first, second year, third years, or some of you might have not yet come across this subject or term, the control system. So let's just see what is a control system in the context of the quadcopters. So the questions to we need to find the answers is, how do quadcopters stabilize by their own? We have all seen they can stabilize by their own. They can stay at a particular pace, lock their position, and not move around like a hovering action. How does a user control the quadcopter? Is the second question. Now, if that is the case, what the real question is, the data from the remote control that we saw is sent to the quadcopter as what and was what commands, usually as what. So the answer to this question we will find in the next slides. All we know till now is there are motors, okay, with the propellers attached. Like I have not shown the propellers in this diagram, but motors are definitely an actuator for us. Now motors definitely need drivers. So it requires the information about how fast you want to rotate the motor to. So RPM or rotation per minutes. So this is the command that goes to the driver. And what do we think user should be placed here? We have four motors for four rotorcrafts in the drone. There are four motors, there are four drivers. Every motor needs instruction about the rotation speed. Do we think user can give the four motor speeds thinking in the mind that, okay, if I want to do an acceleration motion, all four should be same. If I want to do a pitch motion, these two should be fast, this should be low. If I want to do a yaw, okay, counterclockwise should be faster, clockwise should be slower. Can the user in real time have so much complex inputs going to the drivers? No, is the answer. So what we do is, before the user and the RPM, we place a smart guy that can do all these complex things for us. And instead of RPM from the user, we can directly say, okay, I want this angle to be attained. I want 2 degrees pitch. I want 5 degrees roll. I want the drone to face at 110 degrees north, or in that manner. So user can give angles, and the controller, the smart guy, can think, okay, if you want to move in this particular axis, these are the two rotors that have to be faster or has to be lower. If you want to have an acceleration, okay, all four have to be faster or slower. So there is math, there is equations going around, calculating everything, and then finally giving the RPM to the driver. So we place the controller in between the user and the driver. So user gives the angle, the controller finally calculates the RPM and gives it to the driver. But the question is how? How is this so smart? The answer is, if we just place a bounding box around the driver and motor combined, we have the quadcopter system. We need sensors. If we have sensors telling the controller, okay, let's say my goal is to have a 1 degree pitch, 1 degree in the pitch axis. But right now the quadcopter is at 0 degrees leveled perfectly. Sensor, if the sensor can say, okay, you are at 0 degrees, there is a 1 degree error or a deviation from where you want to be at, then the controller can know, okay, I am above, I am in this direction, 0 degree direction, I want to rotate in the downwards direction. That is why I can decrease the speed of front two motors and increase the speed of back two motors. Similarly, if I have the requirement of moving in the upward direction, which is, let's say, -1 degrees, then since the sensor will report, okay, you are at 0, the user gives the angle command as -1 degrees. It will calculate the error and finally decide, okay, I want to increase the speed of front two motors, and then finally rotate and have the the angle achieved. So that is how, with the help of sensors, with the help of what we call as a feedback, so the quadcopter does a rotation, system does a rotation. That rotation can be read by the sensors and fed back to the controller. So it can check in real time, okay, if I have reached the particular angle or not, and finally can decide what to do based on what is the current sensor reading. So this is how, using the feedback or the sensor input, the controller can be smart enough to convert our angle inputs to the final RPM inputs. Now again the question is, can the user still be here? Is it still very convenient for the user to give angle commands to have the quadcopter fly? For example, if I want the quadcopter to just to stay at the position, and after some time I want to move it to a 1 meter on the right hand side, and then lock it there. At this point, is it very feasible for the user? Okay, if I want to move in 1 meter away in the x-axis, x-axis corresponds to roll. Now I want to do a roll action, but how much roll action? What is the angle that I should keep so that the drone rotates at a particular speed and then again comes at 1 meter and then stops and hovers there? So controlling that is possible, okay, but requires inside piloting skills. So it's still not feasible to put the user directly for the angle control. That is why we have one more control usually. Now this controller is called as a position controller. What it does is takes the commands as position inputs from the user. Okay, if you want to be at x-axis in x comma y comma z coordinate, that is the input from the user, and that the position controller will calculate. Okay, if you want to move in x-axis, we will do a roll angle. If you want to move in z-axis, we will do a acceleration the acceleration maneuver. So that's again a little smart for us. The controller is a little smarter. How is the question? Same answer is sensors. Sensors feed back the current position of the drone, and with respect to the current position, it can think about, okay, if I am at 0, if I want to move at 1, I have to do a roll, and as soon as it's moving, its current position changes. The sensor update its position, and as soon as it has reached to 1 meter or wherever the coordinate is, it will say, okay, I have to stop the rolling now. I just will output the angle as 0-degree roll, 0-degree pitch, and that's how the chain is complete. User gives position commands, the position controller decides what is the angle maneuver to be done. Based on the angle maneuver, the RPMs of 4 motors are being decided by the controller of the orientation controller and then fed back to the driver and the motors. So that completes our control system. So this is where we started with the uncontrolled system, and the user now is dealing with a controlled system. This is usually the architecture that we find. The architecture is system is on the rightmost side. We have controllers feeding to the system and sensors feeding back from the system to the controller. That's how the loop completes, right? Controller is giving input to the system is giving input to the sensor, and sensor is giving input to the controller again. That's called a complete loop, or a more or less a closed loop system. That's clear, right? User gives position commands, controller takes care of angles, another controller takes care of the RPMs, and then finally we have the rotation or the hovering angle, hovering action possible. So this is what usually is comprised inside a flight controller software or the firmware. Whichever I mentioned, PX4, Arduino Pilot, Betaflight, iNav, the core idea of the entire control of the firmware is this control system, and other programs dealing with the sensors. Now the question is, okay, I just mentioned sensors, but what kind of sensors do we actually need? Do we need a temperature sensor? Do we need a thermal sensor, a camera? What exactly? So the answer is, since for this controller, the orientation controller, we are dealing with angles, user gives angle to me, or as a controller, user gives angles to me, I have to have an angle feedback. I want to know, okay, this is the desired angle, 5 degrees pitch is a desired angle. What is the current angle? So I need an angle sensor. Can anyone name what kind of sensors give us angle feedback? We all played around with those sensors. We all have in our pockets right now. Can anyone name those sensors? Proximity. Kiran says proximity. Maybe not. Proximity gives you distance between an object. Now he says gyro. Okay, you're getting somewhere. Okay, everyone is saying gyro sensor, accelerometer, maybe something is magnetometer. So you are all correct. What actually is gyroscope is it gives you the angular rotation speed, and accelerometer gives you linear acceleration. I'll not go into depth of gyro and accelerometer, but what I can say is gyroscope and accelerometer combine to form what is called a inertial measurement unit, or IMU. If you recollect, you might have heard this term somewhere. So what, again, I'll repeat, the accelerometer and gyroscope combined forms what is called as a inertial measurement unit, or IMU. We all have IMUs in our phones, in our tablets, sometimes in our laptops also. That's how it can, smartly detect if you have rotated a screen to this particular angle, and then it switches to a landscape mode. Even for games, might have used, for racing cars or for other games, you might have used the function of IMU that detects the angle of your mobile phone. So that's what a sensor that can give us angle feedback or read the angle of a particular body is IMU, and that is what we use for as a feedback for the orientation controller. Done. But how about next controller? Can the IMU be enough for our position controller? Since the thumb rule says whatever is the input for the controller, the feedback has to be the same, apples to apples comparison, right? We cannot have position input and take it, read it back from the IMU, what is the angle? No, there's a mismatch. For the orientation controller, it's angle versus angle. For position controller, we have position as an input from the user. If you want to go at x, y, z coordinate, or move in the x, y, z coordinates, you have to have the same units of feedback, or the inputs or information. So what kind of position sensors do we have? We have gone through it in the slides. Same question. You have the answer in your pocket. In your phone, GPS, Ravi says. Yes, Dr. Ravi says. So GPS, we will use the term GNSS. GPS is for USA. The GNSS of USA is GPS. So yeah, GPS sensors can give us position data, definitely yes. So by other means also, if you can have cameras tracking your position in your frame, and the tracker can give you the coordinates, that can also do your job. So any kind of position controller, position sensor is required for the functioning of position controller. So sensors usually are IMUs and GPS based position sensors, or even other position sensors for the control systems. So that completes our control system and gives you us a brief about what is contained inside the flight controllers. Let's see a more of a higher level plan. So, okay, done. You have angle control done, you have position control done, hovering can be done. But what if I don't want such minute controls? All I want the drone or the quadcopter is to fly around, do a job for me, and complete the mission and come back and land autonomously. So that is what high level planning is. From the user, I just give higher level commands, just go around at particular height, take a photograph, and come back. That's it. I don't care what angles do you fly at, what speed do you fly at, or what coordinates you are moving around. So that's what the higher level planning is usually. If you're not interested in those minute things, is you will choose the autopilot or autonomous system. So this is a example from the mission planner software, and inside that, if you can see the interface, this is kind of a planning for a mission. You have some green color waypoints that are numbered from 1, 2, 3, 4, 5. So basically just drawing a path for the quadcopter or the drone. And then finally you have defined a home position also. And if you look carefully, there are latitude, longitudes, like positions are given, even the altitude is given. So the altitude is 100 meters here. So the mission in general says, okay, go to waypoint number 1, number 2, number 3, followed by 4 and 5 at 100-meter altitude, complete the flight, and then land back at the home position. So that's kind of a mission you can plan. We can classify again these mission plannings or high level plannings in two modes. Autonomous modes are one can be in known environment and can be unknown environment. For example, here it's a known environment. You have the map. You are saying, okay, you have to go here at this particular point, latitude and longitude, at this particular height. So the environment is known, and sometimes the environment can be unknown. So if you have uh, more of advanced missions, for example, just go and survey a particular area. I don't know how the area looks like. I don't know what disaster has happened at a particular area. If a building has collapsed, there's a volcano, there's an earthquake, tsunami. I don't know what the coordinates are. Maybe an unknown environment, and just discover and wander and then come back. And other can be known environments. So path planning, I'll just classify. If there's a known environment and you have to have a planned path from the quadcopter side, you use some kind of algorithms called as A star, Dijkstra, or RRT algorithm, rapid randomly exploding trees. Or if it's unknown environments, and if you still want the autonomous mission, first thing is having an obstacle avoidance, right? How does the quadcopter know if there's a tree or a building or a big obstacle that it cannot go inside? So there is bugs algorithm, bug 0, bug 1, bug 2. Also, there are VFH algorithms. These are specific algorithms for avoiding obstacles. So you can, if you just note down these algorithms, and if you are interested, you can search on the internet. What are these and how do they function? So this is more of a brief about how autonomous flights look like. Now, finally, let's have the last part of the session, which is applications. Nothing new. I'll just touch everything from the surface. For usual application that we see is delivery. Definitely, we have all imagined our future with the quadcopters delivering our parcels in real time, flying around and carrying parcels, right? Agriculture. Today, it's being used. You can spray pesticides, you can spray water, you can spray some chemicals, or you can even go and just survey the crops, survey the yield, get some information about the diseases spread in the plants, or what's the status of the plant, how much is the growth percentage, or things like that. The applications can be found in mapping and photogrammetry. If you want to map a particular piece of land, if you want to see, okay, what is the level of land at what position, so basically entire map of the land, or even have a 3D model made of the entire structure is called photogrammetry. So you can have, okay, this is the size of the tree, this is the mountain, this is the rock. That way you can have a 3D reconstruction of the areas. So you can use your quadcopters and drones for this application. Surveillance, police, authorities, army will use this for surveying around the area, checking for any kind of malpractices happening. Transport, not so intuitive application, right? Since we started with the definition of drone being a pilotless aircraft, now we are coming back, putting a man on the quadcopter and making it a use for transport. So this is not a future. This is actually a real photo. A man sitting inside a particular aircraft, which looks more of a quadcopter, having double thrusters on the four motors. So yeah, you can use it in future. Maybe flying cars can look like this someday. Most commonly used commercially available application is aerial cinematography and photography. This is where weddings, concerts, or even photography, cinematography in scenic environments is done using quadcopters and drones. So that's the most commonly available form of a drone you can buy right off Amazon, with a camera facing in front, and you can have shots taken from the aerial view. But not so commonly known application for drones these days is something called as a first person view drone. Now, what is a first person view drone? It stands for, like, the short form for that is FPV. And all this, the flying of all these kind of aircraft, if you see, it's based on remote control, where you see the quadcopter with your real eyes, and based on that you fly the quadcopter coming front, top down, front, back, and things like that. But if you imagine, if you have a camera on the quadcopter transmitting image to your goggles in real time, not VR, mind it, it's just a goggle, a screen on your goggle that transmits images in real time, and you as a pilot have a view of what the quadcopter sees. So basically, it's as good as you are sitting on the aircraft, and from that perspective, that view, you can fly the quadcopter. So you don't need to have line of sight between the drone and yourself, and that's what is called first person view drone. Now, what that unlocks for us is an application where you can have a very better looking cinematic experience. So this is a video of an FPV cinematic video. These are more agile, more acrobatic quadcopters. You see the movements that they do a free fall, they do a dive, complex rotations you see in the video. The free dive that you saw just now is not usually possible with conventional drones. They just fly, hover around in a direction. But this can be done with this is also a quadcopter, mind you. 4 rotors, same configuration. Just it is very acrobatic. The pilot is having high skills to pilot in this particular fashion. So, good kind of cinematography can be achieved using FPV drones, or else, if I just give an example of cars, we invented cars for our comfort and leisure, right? For transport. But then later, cars also found their application in entertainment, by in racing, F1 racing, right? So since even quadcopters were introduced for certain applications, we found entertainment sources using quadcopters in racing. So same FPV kind of quadcopters, same concept. You have a camera, you have a picture in your goggles, transmitting in real time. You are flying, the pilot is flying with the perspective of the camera in real time, and it goes at very high speeds. They are very agile, very acrobatic. And this is what the video I've just taken to show you what a drone race looks like. These days it's getting famous.
Thumbs up from Chance. Frank's going down the line, making sure everybody's video is good. He's the guy in the white shirt that looks very angry, but he's not. They're ready to start.
Goggles on their eyes.
And we should be off and rolling any moment now.
Around
like a shot, early leader, gonna be the red lights. That is Team Canada. That's the same color they were in the simulator, so.
LFI not
playing games right now. They're playing it safe. They're sticking to their game plan. These other teams kind of pushing it hard off the first lap.
They can go to 500 kilometers per hour. And not
Team and Power Systems in Heart of America chasing hard. But the battle at the front of this one between the red lights of Canada and the green. Thumbs up from Chance. Frank's going down the line, making sure. Thumbs up from Chance.
I will just go back.
Thumbs up from Chance. Frank's going down the line, making sure everybody's video is good. He's the guy in the white shirt that looks very angry, but he's not. They're ready to start. And we should be off and rolling any moment now. Go. Out like a shot, early leader, gonna be the red lights. That is Team Canada. That's the same color they were in the simulator, so of America. Side-by-side action for the third spot. It's a battle at the front and a battle at 7-8 for Team Canada lead lap. 20.2 for Heart of America in the 2 spot, and the only reason he had a bit of a check swing, he's made that gap up now. Lap times this time by.
So that's the racing part that we saw.
Thumbs up from Chan.
And that completes our session. So that's the applications that we saw about the quadcopters, and also touched in brief about softwares, hardwares, and control system aspects of the quadcopters. I am open to questions if you have any in the chat, or if you want, you can unmute your mics and ask the questions. Can you share the PPT? This is available on YouTube, so you can just go back and have the slides getting played on YouTube. I'll check if I can, but you can have the YouTube recording done. What's the cost of making a simple drone is asked by Dr. Ravi. Now, if you are just talking about a very small drone, it has nothing much, doesn't have a camera, or it's not very fancy, you can build it around 8 to 10,000 rupees. As simple as possible, as basic as possible, no fancy things. YouTube live link. I'll just is someone trying to speak? The voice is not audible.
Yeah, sir. Is it possible to design ourselves the ESCs?
ESC. That's what you're asking, right?
I have worked on some drones, sir, but I regularly see ESCs are failing costly. What are the possibilities that made the ESCs fail?
I just repeated question. Is it that you are saying that is it a possibility that we can make our own ESC? Is it the question?
Yes, yes, yes. Because the in publicly available ESCs are failing very costly. That's
Okay.
why is
Okay. So your question is if the ESCs are very costly, can we make our own? That answer
yes,
is yes, definitely yes, you can make because someone has already made it, right? It's just electronics and you have to program the electronics in a particular fashion to drive the motor. You can make your own ESC, but I'll suggest it's very complex. There is electronics, power electronics involved. There is signals involved. You have to have synchronized signals for the
yes,
three-phase
yes.
motors. So that is a
Yeah,
pretty
we need
difficult
to
job.
convert the DC to three phase.
Correct, correct. And that's also it's not just as simple as converting a DC to three phase, because if you want to
Yeah,
have different varying speeds, you have to have different kind of synchronization of the three phases. You can definitely make one. There are so many open options available, platforms to code program your own ESC. But I'll suggest at then the cost at then becomes same, also increases the complexity. So it's better if you go with a something from available
market.
from market,
Sir,
but it's
I have one
pretty
more doubt,
complex.
sir. Sir, I have one more doubt, sir. Sir,
Yeah,
is it possible actually by changing from the change of role and pitch, we need to change the thrust created by the motor actually regular time. But is it possible to just change the direction of motor so that we can travel vice versa? Which is it possible to change the motor direction instead of changing their power? If you can tilt the motor, is it possible to change the roll and pitch
definitely. You are
without
spot
changing?
on. What you are saying is instead of changing the thrust produced by a motor, you just change the direction of the thrust. That is possible.
Yes, yes,
You
yes.
can have the
Yeah,
tilting action over the motors, replace more motors underneath the main motor so that they can tilt the main motors,
yes, yes.
and have the thrust in the lateral axis. This definitely that can be done. That goes to more of a tiltable aircraft, tilt rotor aircraft
Tilt right.
classification. Yeah, there
Thank
are
you, thank you.
things available. It's active research is going around those, and since that it's very complex, since you have to
Yes,
take
sir.
care about the angles of all four motors as well as the thrust produced, so it's the math is a little complex. That's why we don't see
Yes,
that
sir.
that common around.
Thank you, thank you, sir.
So I'll take some questions from the chat. Uh, Question is how much, sir? Can you repeat? So I said if you just want to make a very simple, no fancy, no camera, nothing, a very small aircraft like a more of a hand sized, you can make it around 8 to 10,000 rupees. All you need is a frame, four motors, flight controller, and an ESC. 10,000 rupees or maybe 12,000 rupees, you can achieve them. How can we lose the weight of the drone? I assume you are asking how can you make the drone more lighter? Is it the question? Then definitely the answer is very simple. Choose lighter parts. Choose lighter chassis. Do not choose heavier parts. Okay, so there's a question about certificates. We have to attend. You saying you have attended the past workshops but not got certificates. I think you have to mail your query to support@e-yantra.org. Your query will be answered on that because I'm not aware about the certificate process right now. Which simulator is best for drone piloting practice? There are a lot. So it depends on what kind of piloting do you want to do. One that I used for my training was called as lift off. LIFT, lift and off. Lift off. There is DRL, Drone Racing League Simulator. There is Velocity Drone, and there are more couple of them. Even Microsoft flight simulators have quadcopters or drones. So there are a lot of them you can Google, but this is I think out as the best one. I personally used Liftoff. How can we handle octocopters? So as we defined the different motions possible by the rotation of four motors, and then we have a control over the four motors in a particular fashion. Similarly, you can have the motions defined, roll, pitch, yaw, how to achieve them using eight motors, since you don't have only four now. So similar kind of process you can complete for octocopters and write the similar controls for octocopters. What are some considerations to keep in mind when selecting the appropriate motors and the propellers for quadcopter to build? So the consideration to keep in mind is what is the thrust created by those propellers and motors combined. So propellers and motor combined, I will call it as thrusters. And before buying them, just have to find the data sheet of the particular motor manufacturer, as how much thrust is generated by these particular propellers and motors. So depending on your weight that you want, you have some weight in your mind, or okay, I want to take 1.5 kgs maximum in the air. Definitely divide by 4 should be your capacity of at least should be the capacity of your motors, and even more than that to make it actually accelerate and hover. What's the least price to make a drone? Now you can have it done in 6,000, 8,000 depending on quality of parts you choose. You can have DC motors which are cheaper and make it cheaper. If you have BLDC motors, they will go more expensive. Please explain more about the drone hijack system. Now, even I am not aware about exact process, but I can tell you the possible, methods. So let's say if depending on the drone, how it is being operated, if it's remotely pilotly operated, then let's say it's like there's a communication between the remote control and the quadcopter, right? So the radio frequency at which they are communicating, you can just jam that frequency with jammers, and that communication try to block the communication between the pilot and the drone. That is one of the way where the pilot loses the control over the drone. Or else you can, if it's autonomous, it does not have a pilot, because right, it's autonomous, it's not flying by a pilot, it is doing its mission. So in that case, either you can again jam the same frequency which it's using for receiving the communication from satellite for GPS or GNSS. So if those frequencies, if you jam around in that area, then you can make the quadcopter lose its position feedback and it will eventually crash somewhere. Or else final is physical hijack system. You just fly around a bigger drone and just attack it physically by throwing nets, or even just sacrificing another drone to crash it. So I'll not go into detail about that because even I don't know, but these are some possible means. Can we build a drone with which lifts up to 500 grams? Yeah, you can have very small quadcopters also. What else do we have in chat? How to handle bicopters drone? So bicopter, actually, since the law says that you have two actuators, you will only have independent degrees of freedom. You will have to have some kind of more actuators, as someone suggested, can be placed tilting action in the rotors. So even the rotors are two, you can have more actuators to tilt the rotors. And with that, if you have the two rotors tilting in different axes, then you can have the control over the other axis. So you can have servo motors or some kind of tilting mechanism underneath the bicopter or two rotors, then you can have control. What are the basic things we should consider while construction of the drone? I think I mentioned the components required, but to consider is you have to start with your desired weight. So start with the desired weight, find appropriate motors and propellers that can handle the weight, and then depending on the size of the motors or the propellers that you got, maybe choose the frame and proceed from that part. What language needed to learn program for making a... Does anyone have some question? I'm trying to speak. Okay. So what language is needed to learn programming for making a drone more efficient in software side? Usually the flight controllers are written in C++. If you write it in maybe in ESP or other Raspberry Pi, then you need Python maybe for that. But usually it's C++. Sir, in AI-based drones, can you tell about self-driven system in that drone? So there is nothing like AI needed for self-driven drones, as we just saw. The quadcopters, if it has sensors, enough sensor, it can it can trace its own position and do the maneuvers given the equations are fed inside. You don't need AI exactly to have the quadcopter autonomously flying. If you just want smart cameras and you want to have an artificial intelligence, then you can have more computers. So right now there is no computer as such, intelligent computer that can run AI. You can add Raspberry Pi, you can add NVIDIA boards, you can have such kind of computers, and with that you can put your AI also on the quadcopters. So someone just asked what is the language needed to learn to program the drones. So I just like to introduce at this point the theme, this year's the drone theme that we have in the robotics competition. Every year since the past 5-6 years, we are having a particular flavor of the competition in the drones ecosystem, in the quadcopter ecosystem, where we try to teach different aspects of the quadcopters, its control systems, its high level planning, it's the language that you want to program, and things like that, mission planning in the competition itself. So the competition is a 6-month long competition where you you don't need any kind of prerequisites. You don't need to know anything, any kind of language. All we do is we'll give you tasks and some resources to complete that task. So based on those small tasks, progressively you can build upon those tasks and learn things slowly to finally complete a bigger problem statement. And that's what we teach in the competition. So every year we have drone based competition. This year, since the space theme is being launched, it is a gamified problem statement around the space theme. And usually what is done is for 2 months you do it in simulator. So you prove that you have learned enough things and you are being able to do a task properly in a simulator. Then if you qualify for the stage 2, you get the hardware from our side. You get a drone for free of cost, which you can use to complete the further tasks, compete in the competitions, and if you win, you get the prizes and even internship in IIT Bombay. So this year's theme is called as the name is Luminosity Drone, where we have the concept of an infrared camera or thermal kind of camera. You can go to the competitions page, which is e-Yantra, like portal.e-yantra.org, and read about this year's drone theme. As in the screen, it's mentioned that the scenario that we are dealing here is you have to track the different form of life on an unknown planet. So usually life organisms have a different radiant in the infrared spectrum. So you can, as we all radiate a particular temperature, heat, and all animals do mostly. So that's you have to use the thermal camera on board, track the animals, identify them, and point out their locations. So that can be done in the gamified scenario. For the drone, you will have an actual drone which has an actual camera on it, and you have to learn how to program the entire mission, take the images from thermal camera, read them, process the images, and find the sources of heat and report it to the ground station. So that's what the problem statement of this year is: Luminosity Drone. Technology stacks that are involved is drone building. Obviously, you will be assembling a small drone kit. Control systems, you will be writing your own control systems as explained. You will also do some image processing because there's a camera involved. And tools that will be used is robotic operating system, robot ROS, that is getting famous these days. Simulation, gazebo simulation. The language will be Python usually, and OpenCV tool for image processing. So the ones who are interested to learn and get started with quadcopters, you don't need any kind of prerequisites. All you need to have is have the determination to learn and complete the tasks given the resources. I just point out then a fact that you have to be a student for participating in this competition. Any year student, first, second, third, fourth year, any year is fine. I'll come back to the questions. What is the best controller for the drone? Now, there's no such answer, best controller, but usually if you have an autopilot system, you go for a Pixhawk based or a Arduino pilot based controller. If you are using a controller to control the position, as we are giving input as position, we are not required to calculate RPM for each rotor. I don't get your point. Since we saw the control system were like a stage control system, first stage is position to angle, second stage is angle to RPM. So we need, we don't need to feed RPM directly. You just have to give positions directly if you have a position controller running. Can you see about luminosity drone? I just covered that point. If we are using a controller to control position, as we are giving input as position, we are not okay. That's done, I think. How to punch our code into controller? You have your micro USB port usually, so that interface you can write your own code and push the code into the controller. For computation, can allowed to use existing controller, or we have to design your own. The hardware will be given to you. You will be getting instructions carefully, but you will not be using a pre-made controller as such. You will be writing a small part of the control system, which is the position controller. So angle controller is given to you, and all you have to do is write your own position controller. So that's what the current theme comprises of. The problem statement is to make the drone fly in position space autonomously, and then do a particular path tracing, and then also read the camera at the same time and report. Nandini is saying repeat yaw motion. So I will just okay, should I share the slide if you want? Okay, I will just do it. Okay, I think at this point we might be closing our YouTube session, so I will just sign off from the YouTube. Thank you everyone, whoever has joined on the YouTube live. If you have any questions, you can ask in the comments, or maybe just find on the internet maybe. Or if you're interested to learn things, you can definitely take part in the competitions. So thank you everyone who has joined on YouTube. For people in WebEx, I'll continue. So as you said, what is, how can you repeat the yaw motion? Like quickly, just brief about yaw.